In the last section, we took a look at integration techniques numbers 8 and 9 on our list of techniques that we've been forming here. And what we saw that was kind of surprising at the end of that section is that there were actually going to exist integrals that could not be evaluated using what we called simple or simple elementary functions. Now, one example, and our really key example of something like this, was our integral of e to the negative x squared. That finding an antiderivative of e to the negative x squared is not just difficult to do, but it is impossible to do with elementary functions. And so we really have to try to understand what can we do with functions like this. How do we start to work with them? And is there anything I can do to at least try to figure out an area under a curve for a function like this? And all of these ideas here are going to be helping to guide us towards this final mysterious 10th integration technique, which will take the rest of Chapter 3, Chapter 5, and Chapter 6 to develop. So as we start taking a look at the notes here for section 3.6, you'll see that again, right at the top, I go back to this integral of e to the negative x squared. And the question that we were interested in asking at the end of the last section was, how is it that I could possibly calculate an area under this curve to a high level of accuracy? Remember, if I can't find an antiderivative of this function, then I'm not going to be able to go ahead and use the fundamental theorem of calculus. So how do I go ahead and actually work on evaluating this integral? Well, what we'll see in this section is we're going to have to do a lot of different approximations, going all the way back to almost where we started the topic of integration in a Calc 1 class. We're going to be dealing in this section with approximating areas under curves using actually 3 different types of figures. We're going to be using rectangles, and a midpoint rule, as you can see listed here. We'll use trapezoids, and we'll also talk about using parabolas in a strange way to help us try to approximate areas under a curve.